Swayam Prabha. Digital India. Educated India.
Good morning. This is the third lecture on CFD and Turbomachinery. Contents. I will present today different case study illustrating analysis of flows to turbomachinery via CFD. Case 1, heat transfer over turbine blade. Case 2, comparisons of France and LES. Case 3 would illustrate LES of stator rotary interaction, illustrating interaction of wake on boundary layer. Case 4, vertical axis wind turbine. Case 5, recent approach of turbomachinery analysis. And then I'll present an approach illustrating full engine simulations, followed by concluding remark. Predicting transitional flow over a turbine blade is an important issue. Here I'll present a test case that will illustrate the success of an explicitly imposed transition model in a framework of K-Epsilon equations to predict transitional flow and heat transfer on the turbine casket. Then I will present the comparisons of RANS and LES. The case 1 elucidated the heat transfer predictions over a turbine blades via RANS simulations. I have presented in figure the comparison of surface Mach number and heat transfer distribution over a VKI transonic guide vane. Please refer the paper for details. Please note that the guide vane had been tested in the VKI tunnel, and it has been observed that a shock appears towards the turning edge based on the back pressure. Furthermore, if the large percentage on the suction surface flow is transitional, and it's very difficult to predict accurately the transitional flow and heat transfer with turbulence model. Here, what we have done, we have explicitly imposed some model for transition in the framework of low Reynolds number K-Epsilon model, and it appeared that that explicitly imposed model for transition is successful in predicting the heat transfer. The algorithm used was Jensen 1981, along with local time stepping, residual smoothing, and multigrid. This is the isocontour of Mach number distributions, indicating that a shock appears near the trailing edge on the suction surface, and it's compared well with the experimental observation. Furthermore, when I have compared the surface Mach number distribution for different exit Mach number, it appeared that the computation results agree well with the experimental observation. Furthermore, I have evaluated heat transfer for different free stream turbulence level. I have considered the turbulence level as 4% and 6%, and it has been seen that at 6% the prediction is very good. It's compared very well onset and end of transition, illustrating the augmentation of heat transfer on the suction surface. However, at 4%, the comparison is not that well. It has predicted an early onset. On the pressure surface, the flow remains almost laminar, and for both the free stream turbulence level, and it compared well with the experiments. Thus, overall, I can say that explicitly imposed model for transition is successful in predicting the flow and heat transfer over the VKI guideline. I have already explained about importance of domain, boundary condition and mesh, but let me again remind you that you will have to decide a proper domain, impose a proper boundary conditions. Furthermore, we'll have to generate the grid where grid uniformity, orthogonality should be maintained, while you need to stretch the grid towards the wall or near the leading and trailing edge to resolve the gradient of flow, the velocity, turbulence, quantity. Well, case 2 illustrates a comparison of RANs and LES. The same turbine guide valve is used here for the comparison. The numerical scheme for RANs was based on Jameson, while for LES, the convective fluxes are computed with a fourth order centered scheme, considering a minimum artificial dissipation as proposed by Jameson. Here I have illustrated the contour of density, indicating that for some back pressure flow is subsonic, while for some imposed back pressure of the cascade, a shock appears on the suction surface. And again, as you increase the back pressure, there will be a strong trailing edge shock. Apart from that, there will be some disturbances on the suction surface. So this is with respect to RAN's results. However, the flow field within the turbine passage appeared very different with LES, and the physics here is very enriched. When isocontours of density gradient are presented, it resolves the shading of vortices behind the blade, appearance of acoustic waves within the blade passage, apart from formation of shock on the suction surface. Some vortices appear on the pressure surface because of acoustic waves disturbances. Thus, this kind of unsteadiness has not been predicted with RAN simulation. I have concluded here with the comment that the unsteadiness of flow is well resolved here with LES illustrating the vortex shading behind the vane trailing edge and emission of associated acoustic waves that impact the suction sites. All these details were missing from RAN's data. Therefore, the LES only can predict details such as acoustics waves, unsteady vortices apart from formations of shock or shock bound layer interaction such as indicated here. Prediction of unsteady flows in turbomachinery is very challenging, particularly when Reynolds number and turbulence intensity are high. I would present here a case where we have resolved the blade-wake interaction for a low-pressure turbine blade. Here, LES is needed to resolve the flow fit. And another case, I'll show the unsteady flow which has been developed due to the rotation of a vertical axis wind turbine. Here, U runs along with some appropriate turbulence model is successful in predicting the flows. In case 3, I have presented large eddy simulation of stator-rotor wake interaction, which is an important issue in multi-stage environments. I have considered here a high lift, low pressure turbine blade, where the blade height is considerable. Wakes set from upstream blade rows interact with the downstream blades and make the flow and the bubble forming on the suction surface highly unsteady. The periodic passing wakes interacts with the boundary layer and thus the flow is really enriched in this case. I have used here a highly resolved LES. Thus, a refined grid has been used for this case, where the grid number was around several millions within the blade-to-blade plane, and the total grid required to resolve the upcoming wakes and the following blade passage, considering both, it was more than 12 million grids. The dynamic model proposed by German et al. In 1991 and modified by Lilly is used here for the simulations. The approach was successful in resolving wake-induced transition. It has illustrated the periodic wake as passes over a turbine blade induced unsteady environment where the transition is multimodal. Multimodal transition means that different mode of transition can coexist at different part of the blade passage which appears very complex, and this complex environment has been successfully resolved by the alias. There are number of papers appeared on the subjects in the journal of ASME. If someone is interested, I'll request to go through those papers for details. I have presented here the instantaneous flow field from the alias data, illustrating with distortion, orientation, and staging inside the blade passage. Please note that the wick is staged near the pressure surface, while abundant small-scale eddies appear, augmenting turbulence near the suction surface. And these highly turbulent patches will periodically flow over the suction surface, exciting boundary layer. What appears because of this periodic excitation, there are multimodal transitions. That is, different mode of transition can coexist, which is very enriched. I have not presented other details, but I like to tell you here, please appreciate how LES is successful in resolving the instantaneous development of abundant small-scale eddies, their growth as they contract within the blade passage. If someone is interested, as I have told earlier, please refer to the papers which were published in Journal of Turbomachinery or Journal of Fluid Mechanics, ASME, on the subject. In case 4, I have presented the simulation of flow due to rotation of a vertical axis wind tunnel. This is the construction of a vertical axis wind tunnel where the blades are aerofoil section and which are being rotated at different speed. So figure 5 indicates the schematic of a vertical axis wind turbine. So when it is rotated at different RPM, the instantaneous flow structure would depend on its rotational speed. I have indicated here the flow structures at a relatively low RPM, where this being the flow structure when RPM is increased. You can appreciate the wake shed by one blade in interacting with the other during the course of rotation, and the vortices that will be shed, the structure would be completely different at relatively lower RPM as compared to the situation when RPM is increased. Here one can appreciate the flow field is highly unsteady. Numerical simulation has been made using a commercial flow solver ANSYS. So pressure-based solver has been used in this situation. So URANS is being utilized with a K epsilon's turbulence model. And Urans here appeared successful in predicting the unsteady flow. Most of the computational technique developed so far for the design and analysis of turbomachinery are limited for component simulation. What does it mean? That is, we are successful in simulating flows through multi-stage compressor, turbine, and combustion chamber separately. Now the question is it possible to perform the full engine simulation, that is, conducting the analysis of flows through compressor, combustion chamber, and the turbine together in the same platform? It appears very futuristic. However, MIT has already developed a platform where such a simulation is possible. They have integrated the ideas from different directions, maybe different flow solver, on the same platform, and through a massive parallel computations, they have indicated that such a futuristic simulation is also possible. Thus, I'll now discuss all these ideas to make you understand the effort at present is going on for the full engine simulations. In case 5, I'd like to discuss about the recent approach of turbomachinery analysis and design through CFD. The use of CFD in gas turbine design is limited to component simulation. This is because that the model to represent a large variety of physical phenomena encountered in a gas turbine engine demands a specialized and optimized approach for each component. Furthermore, it should be noted that these flow simulations are typically based on Rand's approach. In Rand's approach, the unsteady flow field is ensemble averaged and thereby removing all dependence on the details of small-scale turbulence. Therefore, a turbulence model becomes necessary to represent the portions of physical stresses that have been removed during the averaging process. Furthermore, in order to predict the complexity of flows in turbomachinery, various parameters in the turbulent model must be tuned or adopted such that, as an example, I can say it can predict transitional flow. This I have already indicated that while predicting transition flow, we incorporate some modification or addition in the turbulence models. On the other hand, the flow in the combustor is characterized by detached flow, chemical reaction, and heat release. The prediction of detached flow and free shear turbulence is significantly improved using the flow solver based on large eddy simulation. An attempt to simulate the multi-component simultaneously required integrating two approaches in a single solver. The idea of coupling RANS and alias methods, evolving a alias-RANS hybrid technique, appears a unique approach in this direction. Moreover, other alias-RANS hybrid approaches, such as detached eddy simulation, DES, combine LES and RANS in a single flow solver. This approach of combining two existing flow solvers has a distinct advantage that it provides the possibility of running simulations in different domains at different time steps and provides a higher degree of flexibility. I have already indicated that the status of present-day CFD applied to turbomachinery design and analysis is limited to the component simulations. With the ability of component simulation, I'll tell you here an approach how to simulate the whole engine, suppose compressor, combustion chamber, and the turbine together. I've indicated here that the compressor, the characteristics of flow there demand simulation of RANS with the turbulence model, while the combustor demands an highly resolved alias to capture the mixing of flow, turbulence, generation, and heat release. Furthermore, again the turbine section, the RANS simulation with an appropriate modeling, perhaps something with transitional flow, is more desirable. So following the characteristics of the flow, what I like to tell that the RANS simulation with an appropriate turbulence model is preferred for the compression and the turbine section, while the computation in the combustors prefers application of LES. So I have indicated here an approach of decomposing the engine component while simulating the entire engine together with compressor, combustor, and the turbine. Here what has been done, the simulated result from compressor is passed to the combustor section through an interface, and similarly the results from the combustor will be sent to the input of a turbine through an interface to do this full engine simulation. Maybe with the application of MPI and message passaging technique, we can perform the simulation together where different solver may run simultaneously and the exchange of data can take place between components to do the entire simulation. Otherwise, it's not possible to go for the simulation of a full engine. In the next slides, I'll show you an approach, where I have shown you how the whole engine simulation has been conducted. That's through an example. I'm sure that you have appreciated that the complexity of engine applications in a gas turbine requires robust and user-friendly coupled solver such as RANS and LES to perform a full engine simulation. So with this discussion, I learned how to conduct a full engine simulation, resolving the flow characteristics in the compressor, combustor, and the turbine. I'll present now an exciting concept, how to simulate the full engine. The coupling of software modules that was developed at MIT is referred as coupler of high performance integrated multi-physics simulation. SIMS. A script based on the Python language allows the communication between solver and SIMS. This arrangement permits more freedoms in implementing and communicating between different solvers and their function in several domains. The results of an integrated multi-component simulation of Pratt & Whitney aircraft engine are presented in the next slides following the approach. The results of the entire engine simulation on a single platform following the approach as developed in NIT is presented here. This is indeed exciting. It illustrates how the flow property changes within the compressor and then in the combustion chamber and followed by the turbine. You can appreciate the mixing and violent turbulence augmentations along with the heat release in the combustion chamber, and also the nature of the flow in the turbine and compressor, where smaller scale eddies, blade-wake interactions, setting of wakes behind the turbine and compressor blade rods are being resolved, and this is indeed exciting by appreciating that such a massive simulation on a very realistic engine has been performed in a single platform coupling different solvers. Same results of the entire engine simulation, but in three-dimensional views are presented here, where you can appreciate the small scale eddies resolved in the combustion chamber. With this, I'd like to say that Even different components has been simulated together, considering a massive simulation. However, the resolution of flow is considerably good. Concluding remarks. CFD techniques for turbomachinery have reached a high level of maturity. Runs with turbulence model have routinely been solved to analyze and design a variety of machines such as pumps, hydraulic turbines, aero engines, compressors, turbines, combustors, propeller, steam turbines, and rockets. The potential for resolving the complex flow physics in turbomachinery has been recognized by recent developments in LES and DNS. These are possible because of improvements in computation architecture. Further advancements in physical approximations, models, numerical methods must be acknowledged. However, there are many uncertainties in CFD predictions of turbomachinery performance, and this must be addressed. Some of the errors are due to the limitation in modeling, some are due to unknown geometry and unknown boundary conditions. Hence, the CFD result must be well validated against experiment. Despite these limitations, CFD remains an extremely valuable tool for turbomachinery analysis and design activities towards the LES and LES-RAN hybrid technique must be encouraged to resolve the unsteady flow through turbomachines. I am towards the end of the course, and this is the time for acknowledgement. The objective of the course is to provide a framework to analyze different turbomachines through a unified approach. The course includes fundamentals of turbomachinery, similarity analysis, cascade flows, axial flow compressors and turbine, centrifugal machines, propulsion, steam turbines, hydraulic machines, and cavitation. CFD applied to turbomachinery is also discussed in brief. The course is developed during the pandemic and mostly voice over PPTs that has some limitation. Such limitations in voice or video quality, please be excused. I'd like to thank the members of NPTEL and TAs for their cooperation and help. Last but not the least, that I'll be happy if the materials presented here are beneficial to graduates and young professionals in the community. With this, I'll wind up the course. Thank you for listening.